Alrighty, so today we are going to be talking about equilibrium, and we're going to get an introduction to some terminology and ideas that are associated with equilibrium. Just a heads up, this is kind of a complicated subject, and so you're going to want to pay close attention as we go through it. So, reaction rates. All reactions occur at different rates. What this means, so for example, striking a match causes it to erupt into flames almost immediately, whereas converting dead plants under the surface of the earth into coal takes millions and millions of years. Reaction rate is the measure of speed of any change occurring within an interval of time, where the interval of time can vary. And reaction rate is measured in amount of reactant changing per unit time. So the key thing to remember with equilibrium is that different reactions occur at different rates, and that's going to play into what we're going to be talking about. Okay? So, the rates of chemical reactions are related to properties of atoms, ions, and molecules through the concept called collision theory. So, collision theory states that atoms, ions, and molecules can react to form products after colliding with each other, providing the colliding particles have enough kinetic energy. So this is something that we've talked about in the past. We've talked about in regards to reactions. Chemical reactions occur through collisions of atoms, ions, and molecules together, and that as long as they collide with enough energy, they're going to be able to form those products. So that's what collision theory is. Now, when we say that it has to have enough energy, we're talking about what we've talked about in the past, the activation energy. Activation energy is the minimum energy that colliding particles need in order to react. So it's that hump that we have to overcome in order to become products. And when two reactants with necessary activation energy collide, a new entity, the activated complex, may form. Okay? So we've seen this graph before when we were starting to talk about thermochem, when we were talking about reactants and products and delta H and activation energy. Now, the activation complex, or the activated complex, is an unstable arrangement of atoms that forms momentarily during a reaction, if the particles have sufficient energy and are oriented correctly. So it doesn't always form, and if it does form, it's only momentarily, so it's only for a moment. The activated complexes have an average lifetime of approximately 10 to the negative 13 seconds. So again, momentarily, very small lifetime that they have. The activation complex ends its life in either the formation of products or reactants. Either outcome is equally likely. Okay? So in a reaction, the activated complex, when you get to that hump, it's either going to go back down to the reactants, or it's going to go the other direction and form products. Either of those reactions is equally likely. That's something that we really need to think about, and that we're going to start talking about now as we talk about and go into equilibrium. So every chemical reaction proceeds at its own rate, naturally, some fast and some slow. By varying the conditions of the reaction that the reaction is occurring in, the rate of almost any reaction can be modified or changed. The following can affect reaction rate. By changing the temperature, we can affect reaction rate. We can affect it by changing the concentration of reactants or products. And in the future, I will be using those brackets if I'm talking about concentration. It's a nice little shorthand chemists use. So if I have a number in those brackets, I'm usually talking about a concentration. And sometimes I shorthand concentration to those brackets because it's a really long word. You can also affect reaction rate by changing the particle size and by the use of a catalyst. So we're going to talk about that. So let's talk about temperature. As you increase the temperature of a reaction, the reactant particles start to move faster and more chaotically. With this moving faster comes an increase in the frequency of collisions, so the number of collisions occurring. Because things are moving faster, they are more likely to be bumping into each other, and so therefore the frequency of collisions increases. With an increase in the frequency of collisions, there's an increase in the number of particles with enough energy to overcome the activation energy barrier. So again, because things are colliding more often, it is more likely that there are now more, since there are more collisions occurring, there therefore must be more collisions occurring with enough energy to overcome the activation energy barrier. Now, that doesn't mean that if, let's say, you increase the frequency of collisions by 10 collisions, that doesn't mean that all 10 of those are going to have a high enough energy. However, it does mean that at least some of those 10 will have a higher activation energy, which means that the number of particles that have a high enough energy to overcome that activation energy barrier increases. It doesn't increase at the exact same rate as the frequency of collisions, but it does still increase. However, the effect the temperature will have on a reaction depends upon whether the reaction itself is exothermic or endothermic. And we're going to talk about that next. So here's an example of an exothermic reaction. At room temperature, a bag of charcoal in contact with air is not just going to spontaneously combust. However, when a starter flame touches the charcoal, atoms of carbon and oxygen collide with greater energy and greater frequency. Some of those collisions are of high enough energy to produce carbon dioxide. Heat released by the reaction supplies enough energy to get more carbon and oxygen atoms over the activation energy barrier so that when the starter flame is removed, the reaction continues. So you can put that energy in to get that reaction started, and then since the reaction produces heat, that continues on that process. But that is just for an exothermic reaction. Okay, so I do want to mention that we will talk more about the effect of temperature and how it differs between exo and endothermic when we start talking about shifts in equilibrium. So right now we're just kind of introducing you to the topic. All right. Let's talk about concentration. So the number of particles in a given volume, or the concentration, does affect the reaction rate. So here we're thinking about concentration as the number of particles in a given volume, which is what it is. It's moles per liter. And that does affect the reaction rate. If the number of particles of reactant is increased, the concentration of the reactants increases, and therefore the frequency of collisions increase. You put more elementary kids in a small room and give them a bunch of sugar, because I always like giving kids sugar, apparently. That's my go-to example. If the more kids you put in that small enclosed room, the more they're going to collide with each other. If you take kids out, you're going to have fewer and fewer collisions. But the more kids you put in, the more collisions you're going to have. And the same thing goes here. If you increase the number of particles, you increase the concentration. That increases the frequency of collisions. With an increase in the frequency of collisions, again, there's a greater likelihood that more collisions will have enough energy to overcome the activation barrier, and therefore the rate of the reaction will increase. So again, this is just like temperature, where we're increasing the number of collisions. If you increase the number of collisions, you are now having a greater likelihood of collisions with enough energy to overcome the activation barrier and then become products. So here's an example. In the micromole rocket lab, you held a glowing splint in air and saw that it glowed, right? Okay, a glowing splint will glow in air. Once the glowing splint was put in a pipette bulb full of O2 gas, meaning that there's now a greater concentration of O2 gas, which is an essential component of burning, the splint burst into flame. Okay, so you took it from a situation where there was a low concentration of oxygen, because really there's not a lot of oxygen in our air, there's more nitrogen, and then you put it in a situation there was tons of oxygen, and oxygen is essential for combustion, and that glowing splint burst into flame. Okay, pretty good example for you guys, and one that you've actually seen happen. So let's talk a little bit about particle size. The surface area of a reactant particle affects the reaction rate. With a decrease in particle size, there is an increase in surface area for a given mass. So if you decrease the particle size, you increase the surface area. Increasing the surface area increases the amount of reactant available to react, and therefore increases the collision frequency and reaction rate. So again, it's that idea of increasing product available or surface available to react, and therefore increasing collisions, which means that you've increased the reaction rate because potentially more of them have a high enough energy to overcome the activation barrier. Let's talk about catalysts. Increasing temperature is not always the best way to increase a reaction rate. Okay, sometimes increasing concentration or changing particle size. You don't actually want to do that kind of stuff to some of your experiments. It may not be great. So catalysts can be used as a method of increasing the rate of a reaction. The benefit of using catalysts instead of heat or any of our other methods of increasing the rate of reaction is that catalysts are not used up during the reaction. And they also don't participate in the reaction itself, in that they don't affect what's going on, like they don't become a part of the product or anything like that. But what catalysts do is they provide an alternate pathway. So they don't get rid of an activation energy, they just decrease the activation energy. They provide an alternate, almost like a shortcut. Okay? So it's like going home and you know that there's a shortcut that shaves off 5 minutes of your drive. Now, you're not transporting yourself home. You're not just suddenly going home. Just like with a catalyst, you're not suddenly becoming products, but you're making it take less time, or in this case, for a reaction, take less energy to actually get there. And so you provide that alternate pathway. So here, we provide a lower activation energy, which means that because you've got a lower activation energy barrier, more of those collisions that may not have had enough energy to overcome this activation energy barrier will be able to overcome a lower activation energy barrier. And so now more of those collisions are going into the product side, so we are actually shifting in that direction towards producing products. Now, so far we've always inferred that chemical reactions go completely from reactants to products. That's what we've always talked about. In reality, this is not usually the case. Some reactions are reversible. This means that the following reactions are occurring simultaneously. Reactants going to products, and products going back into reactants. A reversible reaction occurs when both of those happen at the same time. You've got some reactants becoming products and some products becoming reactants, and they occur at the same time simultaneously. That's why it's called a reversible reaction. What this means is, so for example, we normally write SO2 plus O2 becoming SO3 in this direction, but what's actually going on is that we've also got, we've got sulfur dioxide and oxygen making sulfur trioxide, but we also have some sulfur trioxide becoming sulfur dioxide and oxygen again. And so instead of writing these as two reactions, because that would just be ridiculous and a waste of time, we normally write these utilizing this following special reversible arrow. Okay? It's a double half arrow. And so it is not an arrow with a line with two arrows on the end. Occasionally you will see that on a worksheet because that is what Word apparently dictates a reversible reaction should look like. But in reality, it's a half arrow going forward and back. Some of them I've replaced them with half arrows, some of them I didn't, because I am human. Sometimes I just want to take the easy way out. I'm sorry. It's true. But the correct way to do it is by utilizing this double arrow. Okay? And so that's what we will be writing. So if you look at this reaction, eventually the forward and reverse reactions start to occur at the same rate. So that reversible reaction that we've got where reactants are becoming products and products are becoming reactants, at some point these start occurring at the same rate, and this is called chemical equilibrium. And what this means is that there is no net change in the amount of components in the system. So this does not mean that there are equal amounts of each compound. It just means that the amounts are no longer changing. So if you look here, you can see that eventually, so initially I started producing a lot of SO3, okay? This is my forward reaction, producing a lot of SO3. My reverse reaction would be taking SO3 and converting it back, and so I'm lowering my concentration, but eventually it levels off. In my forward reaction, I was using up all my SO2 and O2 to make SO3, and so that started to decrease, and eventually, though, it slows down so that the amount of SO2 is no longer changing. Same thing here in the reverse reaction where we start actually making a little bit of SO2 and O2. Now those levels level off, and what happens is that the reaction, actually I think I say this next here. So this is dynamic equilibrium, where my forward reaction and my reverse reaction are occurring at the same rate. So the same number of SO3 molecules are being formed as are converting back into SO2 and O2. You're not getting a change in the amount of components in the systems. They don't have to be equal. You'll notice that my concentration of SO3 is not the same as my concentration of SO2, nor my concentration of O2. Okay? So it's all equal. All right. Now, unchanging amounts of SO2, O2, and SO3 does not mean the reaction has stopped either. Rather, that the equilibrium has reached what is called a dynamic state. In a dynamic state, both forward and reverse reactions occur at equal rates. So I've got my favorite example. I love this example. I don't know why. Probably because, oh goodness, you guys know I'm here late because this has started. So I made it in paint, and I love paint. It makes me happy. Okay. So what a dynamic equilibrium means is that the rate of the reaction is occurring at equal rates. The forward reaction occurs at the same rate as the reverse reaction. That does not mean, though, that we have the same amount of everything on the reactant side as we do on the product side. So here I've got an escalator, 2 escalators at a mall. Okay, first floor, second floor. On the first floor we have 1, 2, 3, 4 people. On the second floor we have 1, 2, 3, 4, 5 people. Okay, notice how I do not have the same number of people on each floor. However, I do have 1, 2, 3, 4 people going up and 1, 2, 3, 4 people coming down. So as this reaction goes, the number of people going up to the second floor is occurring at the same, and the same amount of people are then going down to the first floor. So while I don't have the same number of people on the first and second floor, the change between them is occurring at the same speed or at the same rate, and so if one person goes up to the second floor, one person's going to come down to the second floor. And so it's that idea of an equal rates. So you don't have the same amount of product as you do reactant, but you have the same amount of reactant becoming product as you do products becoming reactant. Okay? Oh. Okay. So taking a look at the picture again, the number of people going up is equal to the number of people going down. This means that the rate of the forward and reverse reactions are equal. However, the number of people at the top and the bottom are not necessarily the same. Oh, that doesn't equal, okay? And more importantly, 5 does not equal 4, all right? So this translates to the fact that the concentration or amount of reactants and products does not have to be the same in order for a dynamic equilibrium to exist. All right, that's enough of that. We're going to get into more about equilibrium and stuff called the equilibrium constant and stuff like that. So, yay!